Okay, thanks for the opportunity. So this talk is called Stringy Horizons, and it's based on a paper to appear in collaboration with Hong Liu. Consider a quantum dynamical system. We're going to ask the following question. What is the minimal amount of time, t, for which we need to look at the system in order to be able to predict all the rest of its evolution? Well, for systems without information loss, any arbitrarily small amount of time works, and so t is equal to 0. But the point is that for systems with information loss, it can be that t is not equal to 0. Now let's apply this to n equals 4 Superyoung-Mills with SUN gauge group on a compact space at finite or 0 temperature. At finite n, there is an equation of motion for the theory. So there's no information loss and t is equal to 0. But as we take the large n limit, the equation of motion disappears, and instead we land on a generalized free field theory. And potentially for this generalized free field theory, t is not equal to 0. Algebraically, the fact that t is not equal to 0 means that algebras of operators that are supported on the time band may be inequivalent to the full algebra of the theory. So, of course, this definition of t is valid for all values of the 't Hooft coupling, but at strong 't Hooft coupling, something special happens, which is that the theory has a semi-classical holographic dual. And then t gets a geometric interpretation. So, for example, below the Hawking page temperature, the holographic dual is simply thermal ADS. And you can interpret t as the smallest possible size of a time band that is able to generate a full Cauchy slice of bulk operators. On this diagram, you can see that for thermal ADS, this value is equal to pi. In particular, it's non-zero, and that's related to the emergence of a radial direction at large n. But actually, above the Hawking page temperature, something even stronger happens, which is that no matter how large I take my boundary time band, there's always going to be this little diamond here that I'm not going to be able to reconstruct. And this is because the bulk Cauchy slice never fills up. And this is related, of course, to the formation of a bifurcate horizon in the bulk because I'm dual to a black hole. So t equals to infinity, and there's the emergence of a bifurcate horizon. Well, in order to calculate the values of t at strong coupling, we use these pictures. And of course, that's because we had a semi-classical dual. But the point is that we don't need to use these pictures. T is defined for all values of the 't Hooft coupling, and it can be computed as a subtle harmonic analysis invariant of the large n two-point function for all values of the coupling. So in particular, when we go to weak coupling and the bulk geometry becomes very stringy, it's not very clear how to define a good notion of horizon. But what we propose here is that we can define a stringy horizon by asking that t is equal to infinity. So at weak non-zero coupling in the large n limit of n equals 4 Superyoung-Mills, we can compute t, and it's equal to pi at low temperature and infinity at high temperature. So we find that there's an emergent stringy horizon at high temperature, even at weak coupling. Now, t is a very versatile tool to study the stringy regime of holography. It can be computed in a very wide range of theories, and it can also be used to detect violations of the equivalence principle in the stringy regime. Also, when applied to modular time instead of boundary time, t can also be used to diagnose the presence of a stringy quantum extremal surface in the bulk, rather than a stringy horizon. So as a word of conclusion, the jump to t not equal to 0 at large n is the basic mechanism allowing for the emergence of the radial direction and horizons in ADS-CFT, and this even in the stringy regime. Thank you for your attention.
Very good. Questions?
Could you say, if you look at the two-point function in the omega plane, how do we extract t from there?
Right. So you don't need the plane. You just need real omega. And yeah, so the point is that you need to find, so you take the L2 space of the measure induced by this two-point function, and you look at the largest possible width of, according to the time coordinate, for which you can find a function that vanishes on all functions that are supported on this width. So, sorry, it goes a bit fast, but basically it's a property of, it's a measure theoretic property of the spectral density in the omega plane. Maybe an example is if it has equally spaced peaks, then there's a very simple formula that relates the spacing to this parameter t.
Thanks.
Yeah.
Thanks again.